Hi everyone. This is the second video in the series of video lectures refreshing the principle of mathematical induction. I'm Arvindan Vijayaraghavan. I'm an assistant professor in the computer science department at Northwestern University. Great. So in the last video lecture, we saw what the principle of mathematical induction is, and we saw a couple of examples. Okay. And in this lecture, we're going to show why induction is true. This principle of mathematical induction is true. We'll in fact prove it. And then we'll see some variants of principle of mathematical induction. Most importantly, what is known as strong induction, followed by some examples where the choice of induction hypothesis is crucial. Okay, great. So now let's just review what we learned about mathematical induction, okay, before we go into why the principle of mathematical induction is true. So just to refresh, so to prove a statement P of n, this predicate P of n over natural numbers, the two main steps are to establish the base case. So we show that the predicate is true for the first natural number we want to show it for. And then we show that P of k implies P of k plus 1 for k, which means you assume that P of k is true and you derive that P of k plus 1 is true. This assuming P of k is true is called the induction hypothesis. Okay. And then you establish that P of k plus 1 is true. If you're able to do this, then by the principle of mathematical induction, P of n is true for all natural numbers. Okay. Now let's see why mathematical induction is true. So in fact, the principle of mathematical induction is not an axiom or an assumption, okay, about natural numbers. This is in fact something that we can prove using first principles. Okay, and so this is just a theorem. Okay, and we'll prove that. So we'll just prove this mathematical induction. So for any predicate P on natural numbers, okay, suppose P of 0 is true, and this is the base case. And suppose P of k implies P of k plus 1, then for all natural numbers, the predicate is true. Now, we'll prove this by contradiction. This is a proof by contradiction. And many of these proofs by contradiction, let's think about k0 or k0 as the smallest k for which this, for which this predicate is not true. So, okay, so we are proving this for sake of contradiction. Let's assume that there is some k for which this predicate is not true, and let k not be the smallest such k for which it's not true. Now, clearly, k naught has to be at least 1. Well, why is that? Well, that's because by base case, which is A, we know that P of 0 is true. Okay, so k naught can't be 0, so it has to be at least 1. Okay. Now, further, what can we say about P of k0 minus 1? Well, P of k0 minus 1 is also true, since k0 is the smallest violation. By violation, I mean a number for which P of k is not true. Okay, so any number smaller than k naught, those numbers, the predicate evaluates the truth. Okay. Further, by by assumption B, P of K naught minus 1 implies P of K naught. So P of K implies P of K plus 1. So in particular, P of K naught minus 1 implies P of K naught. Okay, that means, so, and we know that P of K naught minus 1 is true. Hence, P of K naught is true. Okay, so this contradicts the assumption that P of K naught is false. Okay, so this is assumption that K naught is the smallest K for which it's not true. Okay, and it contradicts this. Hence, P of K is true for all natural numbers. Good. So what does this mean? It means that any proof by mathematical induction that you're doing is really a proof by contradiction. It's just an extremely convenient tool, a very powerful tool, okay, to go about proving these statements about natural numbers. Okay. I mean, but if you wanted to, you could unroll it out, and you can really prove all of these things that you are doing using induction as a proof by contradiction. Okay, good. So yeah, so this, I mean, so this is a principle of mathematical induction, and it is a very powerful tool to prove true statements about natural numbers. Okay, um, and I mean, while it's an extremely powerful tool which can be used in many different scenarios, it is less revealing than direct proofs. Okay, so sometimes you might be, I mean, often when you're trying to prove the different steps, the base case and the more, I mean, particularly the second step, which is showing that P of K implies P of K plus 1, you are using a lot of intuition about the problem. But oftentimes, the real reason why the statement is true may not be as clear to see in an induction proof. Okay, so when you can get a direct proof of the fact, that's often preferable. But sometimes, I mean, yeah, I mean, but induction is an extremely convenient and powerful technique. And I mean, with all this power, you also have a lot of pitfalls. Okay, and it's there are. I mean, it's quite easy to prove incorrect statements, to supposedly prove incorrect statements by making some common errors in induction proofs. Um, so, for instance, perhaps the most important one is to establish the correct base case. So, firstly, you have to prove the base case, and the base case really has to conform to the. I mean, has to correspond to the statement you're trying to prove. If you want to prove it for all natural numbers starting from 2, you have to start with 2. Okay, it's yeah. So it's kind of important that the base case matches what you're trying to prove. And in the second step, you are assuming that P of K is true and then trying to prove P of K plus 1. You should not do the reverse and use P of K plus 1 to prove P of K. Okay, and this, while this sounds obvious that you shouldn't be doing this, when you write down certain proofs, when you write down what you need to prove and start simplifying from it, sometimes you may reach incorrect conclusions because really what you end up doing is to prove the reverse, okay, which is not what you want. Again, sometimes your induction hypothesis, I mean, your induction hypothesis can't be too strong. So, for instance, you can't say P of K is a statement that it is true for all natural numbers. Your induction hypothesis has to be the statement that P of K is true for the particular natural number K. You can't here assume that it's true for all natural numbers, then you have nothing left to prove. Okay, and there are many other pitfalls that you may face in induction, and this is something that you can in fact look up some of these incorrect induction proofs, and it's actually a fun read to go through some of these proofs and realize the kind of mistakes you can make. Okay, so let's look at some more examples of induction. Okay, in particular, we will look at this technique called strong induction. Okay, so what is strong induction? So um, we still want to prove a statement about natural numbers. So let that be the predicate P of k. The first step is going to be the same. The base case, you have to establish the base case for first natural number, let's say P of 0. Okay, that P of 0 is true. Now, in the second step, we're not just going to assume that P of k is true. The induction hypothesis is not just that P of k is true. We can, in fact, make a stronger assumption that not only is P of k true, we'll also assume that P of 0 is true, P of 1 is true, P of 2 is true, up to P of k. So P of k minus 1 is true, and then P of k is also true. And then, assuming that the statement is true for all natural numbers starting from the base case 0 to k, we'll now try to prove that P of k plus 1 is true. Okay. And if you are able to do this, then by strong induction, this predicate is true for all natural numbers. Okay. So the main place where induction, the simple induction and strong induction differ is in this inductive hypothesis. Okay. So in simple induction, we'll only assume that P of k is true. Whereas in strong induction, we get to assume that it's true for all natural numbers. Okay. Now, so why is this useful? Well, it's because you have more to play with. So you're assuming something stronger. So you're not only assuming that the statement is true for k, you're assuming that it's true for all numbers starting from 0 to k, and now trying to prove k plus 1. So if you have more to start with, more assumptions to start with, you can use more of this information, and perhaps it's easier to prove p of k plus 1 in that case. So this is something is an easier. I mean, it's often easier to prove statements using strong induction compared to simple induction. And as you can surmise, uh, any statement you can prove using simple induction, you can prove using strong induction as well. Okay, because you're just assuming more in the induction hypothesis. So, yeah, there's no reason for you to not use strong induction. But somewhat counterintuitively, it's in fact you can also prove that the principle of strong induction is true by just using simple induction. Okay, and I'm not going to prove it here. You can see this in section 6.3, for instance, of the book by Lehman, Layton, and Mayer. Or actually any book in discrete mathematics will have this. Okay, so let's see an example. Okay, so we want to show that for every natural number, that is at least 2 can be written as a product of primes. Okay, where some of these primes could be repeated. So we really want to prove that it's a product of prime powers. Okay, and we'll show this by using strong induction. Okay. And in the process of the proof, I'll also try to explain why simple induction might not have been. I mean, at least the basic strategy of using simple induction may not have been enough. Okay, so as in any induction proof, I mean, this is first seen as a statement about natural numbers, and here the statement, the predicate is clear. P of k is a statement that k can be factored into primes. By that, I just mean can be written as a product of primes and prime powers. Now, the base case here is just the first natural number for which we want to show the statement, and that is k being 2. So the base case P of 2 is true because 2 itself is a prime. So you're writing down 2 as a product of, 2 raised to the power of 1. So it's a product of prime powers. So the base case is obviously true here. Now, the induction hypothesis is going to assume that the statement, the predicate P is true for all natural numbers starting from 2 to k. Okay, so all of these natural numbers 2, 3, 4 up to k can be written as a product of primes. Okay, sometimes with repetition. And now we want to prove that this is true for k plus 1. Okay, so let's try to prove that P of k plus 1 is true. So you have two cases. Use a different thing. For k plus 1, okay, so case 1, k plus 1 is a prime. This case it's easy because clearly k plus 1 is just k plus 1 raised to the power of 1. So it's a product of prime powers. Okay, so in this case we're done. The other case is that k plus 1 is composite. It's not prime, so it's composite. That means I can write down k plus 1 as the product of two numbers, a and b, where both a and b are natural numbers that are between 2 and k. It has to be less than k plus 1, so it's between 2 and k. Great. Now, what do we know about a and b? A and b are both less than k. So by the induction hypothesis, that I could this with an IH. P of A and P of B are both true. So A can be written as a product of primes or prime powers. B can also be written as a product of prime powers. But K plus 1 is just a product of A and B. So you can use the prime power decomposition for A, the prime decomposition for B, and we are just multiplying them. So hence P of K plus 1 is also true. Since k plus 1 is equal to a times 2. Okay, so by strong induction, sorry, 1 second, this one. Since by strong induction, P of n is true for all natural numbers. This completes it. Okay, so we look at now we earlier looked at simple induction, and we have now looked at strong induction. And the difference is, so in both cases, we first need to establish the base case. But the main difference is in the second step, where in simple induction, the induction hypothesis just assumes that the predicate is true for k, and then we want to derive that it's true for k plus 1. In strong induction, the induction hypothesis is more powerful because you not only assume it's true for k, that the predicate is true for all natural numbers starting from the base case up to k. And then you try to prove that it is true for k plus 1. So here, the 0 is really the base case. So if the base case is not 0, it should start with the base case. Right. Okay, so now let's see why. Let's see some interesting examples where choosing the induction statement will be the right induction statement will be important. So here's a statement about matrices now. It's again not about numbers per se. Let's define, this. So let's look at this matrix given by 2 cross 2 matrix given by 1, 1, 0, 1. Okay. And what I'm looking at is the kth power of this matrix. By that I just mean, and by the kth power, I'm just multiplying the matrix with itself k times. Okay, so a raised to the power of k is just, for numbers, you're just multiplying the same number k times. Here instead, you're multiplying the matrix with itself k times. Okay, and yeah, that's how you define it. So, and the goal is to prove that for this particular matrix, if you look at the kth power, so you want to show that all the entries of this matrix are at most k. Right. Now we'll prove this. We'll try to prove this by induction on k. So what's the obvious induction statement? So the predicate. Predicate is just the statement that P of k is just a statement that all entries of AK are at most k. Now let's try to prove the statement. Let's try to prove this predicate. So the first step is the base case, and the base case is true because A1 is just the matrix 1, 1, 0, 1 raised to the power of 1, and that's that's certainly true because all the entries are at most 1. So hence P of 1 is true. Okay, so that's the base case. Now, so let's assume that this is true for k, or if you want, you can assume that it is true for all numbers. P is true for all natural numbers up to k. So let's say that AK is actually of the form some P, Q, R, and S, and the only thing we know about these numbers is that P, Q, R, and S are all at most k by induction hypothesis. Now we want to show that AK plus 1 also, all the numbers, all the entries of AK plus 1 are at most k plus 1. Now let's write down AK plus 1. AK plus 1 is just AK times the matrix 1, 1, 0, 1. Just multiplying it one more time. And suppose AK was this matrix PQRS, by multiplying it by the matrix 1, 1, 0, 1, you actually get this matrix, which is P plus Q, R, and R plus S. Okay, now what can we say about these entries? We know that P, Q, R, and S are all at most k. So the two entries on the first column, they're both at most k, but the entries in the second column, just based on the information that P, Q, R, S are at most k, to go up to 2 times k. Right, so it's not clear, but we, on the other hand, we want to show that it is at most k plus 1. So we don't know. So this proof, this doesn't quite show that it is P of k plus 1 is true. So, so is P of k plus 1 true or not? This is not very conclusive. Okay, so maybe the statement is just false, that every entry of AK is being at most k. Let's write down some. Let's actually evaluate AK for a few values of k and try to see what happens. Okay, so A1 is actually just 1, 1, 0, 1. A2 is 1, 1, 0, 1 times 1, 1, 0, 1. And if you write this out, this is just going to be, I'm just going to multiply out these matrices. This is going to be 1 times, and then this is 1 times 1 plus 1 times 1, which is 2. Then you have 0 times 1 plus 1 times 0, which is 0. Then similarly, this will be 1. So good, that's A2. Now A3 is 1, 2, 0, 1 times 1, 1, 0. And if you write this out, the first entry is 1 times 1 plus 2 times 0, which is 1. The second entry is 1 times 1 plus 2 times 1, which is 3. Third entry is 0. And the fourth entry is. Okay. So now you see that there's some kind of a pattern, right? So maybe we can actually show that AK is really of the form 1K01. And in fact, if you try to work it out for not just 3, for 4, and so on, you'll see that it is actually true. So maybe this is something that we can actually try to prove. And maybe we can prove it using induction. And if we are able to prove it using induction, it certainly implies the theorem we want to show, which is just that all the entries are at most k. So that's what we do. Okay. So our induction hypothesis is not going to be the one that is obvious from the statement. It's actually going to be something stronger. The predicate will just be the statement that uh, AK is exactly of the form 1K01. The stronger statement than saying that all the entries are at most K. Now let's prove this. Okay, let's establish this for all natural numbers. The base case is easy because A1 is just 1101 and it is of the form 1K01. Okay, equal to 1. Now if you look at AK plus 1, it is AK times 1101 and I've just written it out just to save some time. And if you multiply out 1K01 with this matrix 1101, you exactly get 1K plus 1, 0, and 1. So assuming that P of K is true, so here we this equality is by induction hypothesis. So we assume that P of K is true. So AK in that case has the form 1K01. Now you know what AK is, assuming P of K, and then you can just actually just multiply it out and get the expression, and we see that this is really what we want to show as well. Okay, and so P of K plus 1 is true. So by induction, this is true for all natural numbers. And this implies in turn that all the entries are at most K. Okay. So just a takeaway is that sometimes to prove a statement inductively, you may actually have to prove a stronger statement first. Okay, and the choice of the statement is sometimes quite important when you're trying to prove something by induction. In many cases, you'll just be obvious from the statement you're trying to prove. Sometimes you may want to choose a predicate or an induction hypothesis that's stronger, that might imply whatever condition you want. Okay, this is a little counterintuitive because um, you're trying to establish a predicate that's stronger, but somehow that should intuitively only be harder, but it turns out to help us. And the reason is partly because when you're trying to prove this by induction, in the induction hypothesis, by assuming by trying to prove a stronger predicate, we get to assume more because the induction hypothesis assumes that P of K is true, and there you are actually assuming more about the problem if you have a stronger predicate. Okay, so you might be able to derive that P of K plus 1 is true more easily. And figuring out the right predicate is not easy. Okay, there's some creativity. There's definitely a lot of creativity involved, and often it helps to work out small examples to guess the right induction hypothesis. And in fact, even in research, there are many situations where you can prove your statement using induction, but often the difficulty is in identifying the right statement to prove. And this is something that, yeah, so coming up with the right induction hypothesis is there's a lot of skill involved in it. Okay, so just a couple of quick things to finish it off. So induction is extremely useful in computer science as well, particularly in programming languages and in arguing about programs in general. And one particular use case for induction is improving what are known as invariants. Okay, so what is an invariant? It's something that is not varying or constant, and so it's kind of unaffected by any operation. Okay, and this is very useful in things like program analysis or in analyzing algorithms and so on. Okay, and how do we try to? So you'll try to argue that some property of the program is true throughout the execution of the program or the algorithm, and the way you try to do it is to form the predicate P of K, which really says that the invariant holds after the kth step of the algorithm, or it holds during the kth step of the algorithm. Okay, so now you've turned your goal of proving an invariant about a program as a statement about natural numbers. Okay. And now you can try to show this using mathematical induction. So for instance, you can try to, if you're looking at an algorithm, an example is maybe you want to show that the insertion sort algorithm after k steps would have the first k numbers being sorted. This is a statement that you can try to prove using mathematical induction, where by formulating the right predicate. And yeah, I mean, you can actually prove very powerful statements, particularly in program analysis, by using mathematical induction. And in these lectures, we were only using induction over natural numbers. The domain was natural numbers, but in fact, you can actually extend induction to other kinds of structures as well and domains. In fact, it works for any set where you have this kind of a recursive structure, where the elements of the set can be defined recursively, like if you have a tree or things like arithmetic expressions and so on. Okay, and I'm not going to go into this, but you can look it up if you're interested. And this is often used in programming languages, for instance. And here you'll have a base case that doesn't depend on anything else. Okay, it's like one of the atoms or initial building blocks. And then you have the structure, so like natural numbers, and you have what is known as a constructor, which will tell you how to build new objects from other objects that have been previously built or defined. So any kind of a set that has this kind of a structure is something that you can use mathematical induction on. And in fact, natural numbers also have this structure. You could think of natural numbers as 0 is the base case or the simplest block, and then you keep defining the next natural number as 1 added to the previous one. This is in fact how Peano's axioms define natural numbers, but really induction works for more general sets of this form as well. Okay, so and there are other kinds of more sophisticated versions of induction called transfinite induction, but we'll not discuss it here. Good. Just to summarize, in these lectures, we looked at the principle of mathematical induction, and these were for proving statements or predicates on natural numbers. And while this sounds quite specific, there are many different kinds of statements that you can prove using mathematical induction. And maybe the first step or the 0 step is to identify whatever you're trying to prove as a statement about natural numbers, as a predicate on natural numbers, and then prove it. And we also looked at this, we looked at why induction is true. We looked at strong induction, principle of strong induction. And we also looked at how the choice of the induction hypothesis is often crucial. Okay. Thank you.